Get ready to challenge everything you thought you understood about time. A groundbreaking new study has reached a stunning conclusion: time, as we know it, may not actually exist. According to this research, time is nothing more than an illusion, an effect of quantum entanglement. But what led scientists to make such a bold claim? Today, we're diving into the heart of this extraordinary study to uncover what's really behind it, and how this radical perspective could not only resolve long-standing contradictions in physics but also transform our entire understanding of the universe. Let's begin with a deceptively simple question: what is time? Albert Einstein once offered a profound insight on this topic. For us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. According to Einstein, the concept of now has no objective basis, it's entirely subjective. And as we dig deeper, it becomes increasingly clear that time, which feels so familiar and straightforward in our daily lives, is actually one of the greatest mysteries of all. Most of the time, we think of time as nothing more than numbers ticking away on a clock or a date marked on a calendar. But we rarely stop to consider what time actually is. In fact, many of us would struggle to define it. Is time something physical? Does it exist somewhere in space? Let's explore what the experts have to say. By definition, time is a physical quantity that orders events in a specific, irreversible sequence. This applies universally to everything. Even the universe itself doesn't just expand through space, but also moves through time, from its origin in the Big Bang toward its eventual end. In that sense, time flows in a straight, linear direction. As American physicist John Wheeler famously put it, time is what prevents everything from happening at once. Still, despite our best efforts to understand it, time remains one of the most puzzling concepts in science. It might even be something entirely different from what we've always assumed. As we mentioned earlier, a groundbreaking new study has reached a mind-bending conclusion: time might not be a fundamental feature of the universe after all. Instead, it could simply be an illusion created by quantum entanglement. But what does that really mean? Does it imply that concepts like the beginning and end of this video don't truly exist? Should we erase seconds, minutes, and hours from our dictionaries? Well, it's not quite that straightforward. To understand why time remains one of the most debated topics in science, we need to look at the different perspectives scientists take. On one hand, we have Einstein's theory of relativity, which describes the universe on a grand, cosmic scale. On the other, there's quantum mechanics, a field focused on the tiniest building blocks of reality, often clashing with the rules of classical physics. To illustrate this strange quantum world, let's revisit a famous thought experiment, Schrödinger's cat, proposed by physicist Erwin Schrödinger back in 1935. In this famous thought experiment, a cat is placed inside a sealed box alongside a capsule of lethal poison. The twist? No one knows exactly when, or even if, the poison will be released. Until the box is opened and observed, the cat exists in a strange limbo, both dead and alive at the same time. But why did Schrödinger come up with such a bizarre scenario in the first place? His goal was to highlight the conflict between the principles of classical physics and the puzzling nature of quantum mechanics. After all, in our everyday world, a cat can't be both dead and alive. This leads us to one of the most intriguing aspects of quantum theory: superposition. In quantum mechanics, systems can exist in multiple states at once, until we observe or measure them. It's only through observation that one definite outcome emerges. And it doesn't stop there. Quantum entanglement, another cornerstone of the field, shows just how deeply connected quantum particles can become, no matter the distance between them. In standard quantum theory, particles don't possess a definite state on their own. Instead, they are described by probabilities of being in various states. These probabilities only collapse into a specific state when an observation or measurement is made. While this concept might seem puzzling, it becomes even more intriguing when two particles interact and become entangled. In such cases, their individual probabilities are no longer separate but interconnected. Together, the two particles are described by a combined probability function that represents both of them simultaneously. To illustrate this, consider the following example. In an experiment designed to demonstrate entanglement, two electrons are created simultaneously, and their spins, or intrinsic angular momentum, are measured using two separate devices. Remarkably, the electrons are found to have opposite spins, which is especially surprising because, according to the principle of superposition, their states were completely undefined until the measurement occurred. In fact, it is only upon measurement that one electron adopts a specific spin state while the other instantaneously takes on the opposite state. Despite being physically separated, the two electrons must be viewed as a single, coherent system. Luckily, that's how it works. An important point to consider is that quantum entanglement challenges the principle of locality, which asserts that events only influence their immediate surroundings. In the case of quantum entanglement, however, particles separated by vast distances, sometimes light years apart, remain deeply connected. Even more striking is that these distant particles share information instantaneously, with no delay in time. Given this, it's understandable why Albert Einstein was highly skeptical of what he famously called spooky action at a distance, since such information exchange would need to occur faster than the speed of light. Despite its complexity and the confusion it often causes, quantum entanglement might hold revolutionary answers and help us understand the true nature of time. Could time itself be merely an illusion created by entanglement? In quantum mechanics, time tends to be viewed as fixed and external, whereas in Einstein's general theory of relativity, time can actually be warped by factors like gravity and velocity. In quantum mechanics, time is seen as a fixed phenomenon, a continuous, unstoppable flow moving from the past toward the present. Yet, time itself exists outside the strange and ever-changing quantum systems and can only be detected by observing changes in external references, like the ticking of a clock. On the other hand, Einstein's general theory of relativity presents time as intertwined with space, capable of being warped and stretched. This fundamental discrepancy makes it challenging to unify these two physical theories. To address this gap, researchers at the Italian National Research Council have turned to a concept introduced in 1983 by physicists Don Page and William Wouters. Their Page-Wouters mechanism suggests that time emerges from the relationship between one object and another acting as a clock. In this view, time for any given object exists only through its quantum entanglement with another object that serves as a timekeeper. In a system without quantum entanglement, time essentially ceases to exist. The system experiences the universe as if it is completely frozen and unchanging. To explore this idea, scientists applied this concept to two theoretical quantum systems, one being a vibrating harmonic oscillator, which can be thought of as a simple model for particles in motion, and the other a set of tiny magnets functioning as a quantum clock. Remarkably, they found that the behavior of their combined system could be accurately described by the Schrödinger equation without ever explicitly involving the concept of time. Taking their study a step further, the researchers performed their calculations twice, first treating the magnetic clock as a macroscopic object, meaning something large enough to be observed directly, and then considering the oscillator as the larger entity. In both cases, the complex quantum equations gradually simplified and converged to those familiar from classical physics, the physics of everyday objects. This transition strongly suggests that the very flow of time as we perceive it emerges from quantum entanglement, even at scales much larger than the microscopic quantum world. Published in the journal Physical Review A, their findings emphasize a profound shift in perspective, Rather than trying to explain quantum physics starting from classical physics, scientists should begin with the fundamental principles of quantum mechanics and work toward understanding how classical physics and our everyday experience of time naturally arise from it.